Started. So related rates. So a couple of challenges here is the setup. So translating the information that sometimes is like half a sentence into mathematics, into algebra, and then this is the mistakes. A lot of mistakes happen is where you get to differentiate, and so even if you are used to differentiation by now, then now differentiating functions that have not been specified is just a little bit new, I suppose. New and strange, but just like with a lot of other things in this course, if you do it a few times, you should be able to do it again. So that's the outline is right here. So about the sliding letter. And once again, the words on right, picture helps, identify the variables, specifically then use them as a way to translate the words into formulas. And then just differentiation. The key, of course, is the actual relation. The relation is what makes it solvable, right? So the relation between those quantities that we treat as variables, and then you differentiate. But the actual variable of the with respect to which you differentiate might be hidden. So in this particular case, the variable was time. So only from the words such as how fast, you know that it is where somewhere the time is also quantity. It's never spoken. Now in the picture you don't see that either. So you have to get used to that. Okay, so any questions about this kind of problem? So okay, so I'm gonna so there might be a problem. So was it a yes or no? So it is a good idea to maybe to definitely actually always split problems when it's early on into different parts. So this one includes everything, so which makes it kind of interesting. But on the other hand, it is just too much happening at the same time. So that is why. So you could do almost literally this. There is no letter. There is nothing. All you have is a relation, and this part is the actual part that is the, well, at least one of the challenges. One of the challenges is this. Well, to get to this point, this is it. Okay, so differentiate a relation with respect to a variable which may or may not be present in the equation. So a relation, if you prefer. So x and y are two quantities related to each other as we have seen them before, and that is the difference is right here, like this. It looks very similar. The difference is that here you have x and y related to each other through equation. That's the similarity. The difference is that we declare somewhere, you'd better do it, y is a function of x. Okay, so that is the key, and then that's why you differentiate over x, the dependent variable. So if you know independent variable, then you know how to differentiate. Okay, and then now we're having a problem that looks very similar. The equation is similar. Look at the equation that's circled here and the equation that this one. Okay, rather not this one, but that one. Okay, this. Okay, are you gonna do it? No. Okay, where am I? Okay, this is the equation. This is the equation, and it looks very similar. Relation between x and y, but differentiation happens to be with respect to t, which is determined either by you specified you asked to differentiate with respect to t, then that's what you do, and or you the problem should suggest what is that you're trying to accomplish. So once again. It is entirely algebraic problem, but like what I circled here is the algebraic problem that we're solving. The bottom is pretty much the relation between the related rates. Well, there's one more step. Well, from here I could have proceeded to dy dt. because dy dt was the actual question to be asked, and you solve for dy dt, and that's how you have the answer. Okay, so let me do it one more time, maybe. Of that, once again, that problem without the words. So let me do two. So differentiate side by side. Say xy plus y squared is equal to 0 with respect to x. And then I'll do with respect to y. Well, how about I do both? And t. Okay, so t then, when you say with respect to a variable, you indicate that that variable is the independent variable. So either it is x that is present here, or it is t that is not present. So let me just do them side by side. Because in many ways it's similar. So I'm differentiating with respect to x. Once the variable is chosen, write it. That's what Leibniz notation is good for, to actually indicate the variable of differentiation and the independent variable. So it's xy plus y squared is equal to d dx of 0. So once again, two functions equal to each other, the derivatives are also equal to each other. Okay? So split it, d dx xy plus d dx y squared is equal to 0. Once the easiest step is done, y appears in each of these terms every time the variable that is not the independent variable will be then treated as a function, and therefore its derivative will appear. Okay, so you do not think of you do not differentiate with respect to y. Okay, so what do we do with the first term? Product rule. Okay, so two terms, x and y, differentiate the first one. So I could say d dx of x times y plus x times d dx of y. Okay, that's the first term. And then let me carry it out. So d dx of x is
it 0?
No, it's 1. Okay, times y. And then d dx of y, it is simply dy dx. Okay, I just moved it. It's a differentiation of y with respect to x, and since we don't know what y is, we just write its derivative. Okay, so that's the first term. The second term is what rule do we apply for the second term? What? A power? The power rule, yes, but there's a more important rule here. The chain rule. We are not differentiating with respect to y, we differentiate with respect to x, which means y is a function, which means that we are looking at a composition. So what's the answer? So the trick is really not complicated. You do differentiate as if it is you differentiate with respect to y, but then, according to the chain rule, also its derivative reappears. Okay? So that's it. 2y dy dx is equal to 0, and frequently what you ask to do is to solve for y. So let me just quickly write what it is. Dy dx will be, what is it? Y divided by x plus 2y. Okay? So in other words, we're talking about an equation, the equation that represents an implicitly defined curve What that curve is, I have no idea, but it doesn't matter because things work out anyway, just algebra. And then so we found if we necessary, we can use this to find tangent lines. Okay. So let's do the other one, which is also related rates, but there's the third variable here that is t, and which means that we are talking about differentiation with respect to t instead. So side by side, d dt xy plus y squared is equal to d dt of 0. Okay, so the pattern is the same up until some later point. Everything else is the same. So I'm using the sum rule once again to split it. So I'll have d dt of xy plus d dt of y squared. Still 0 on right. Product rule. Once again, also it's kind of in a way that does not really require any thinking, just pure application of the rule. So as long as the challenge is to know which rule to apply, and then at least early on, if you just write it out and then see what happens. So I'm writing out the product rule for this. So I'm just writing d dt of x. Look at it, it's almost exactly the same. So only the denominator of ddtx becomes ddt. That's the only difference. Times y plus x dt of y. And then, so that's the product rule. That's the product rule. And then, okay, so what's next?
Would that not be too loud?
Okay, tell me what the third term is. Okay, well, let's do it the same way we did last time. So let's take care of these two terms first. ddt of x is, see, there is no match of the formula x in the independent variable x anymore as we had on left. Now we are differentiating x with respect to t. X is a function of t, so what is it? dx dt, yes. dx dt, y, okay. And the second term, x times what? dy dt, okay. So as you can see, it's even easier in a sense because x and y are now fully equal. They both depend on t. Okay. Now the third term is once again we're treating them once again with the chain rule, and it is similar. So once again the trick is of chain rule differentiation is to differentiate the two functions that are composed consecutively. So the function that you can see on the outside is y squared, so that is the one that is being differentiated first. And so once again I have 2y. But now it's different, it's multiplied by the derivative of the function on the inside, which is y. So what is it? No. dy over dt, yes. Okay, so and that after that there is really not much. We could still solve for dy dt, I suppose. Let me solve for dy dt. So dy dt is once again dx dt y divided by x plus 2y. So you can see the difference is really not huge in it's still differentiation. The main difference is, in fact, easy to point out. This is the main thing right here. That is the only term that is appears and looks different. It is 1 on left and it is not 1 on right. But why? How do I turn, if I start on the right, and how do I turn everything as what's on left? I just take every dt and replace it with dx. If I take the solution on right and replace each dt with dx, they all will be in the denominator. Then the only that extra, everything will work out easily except for the term that I underlined, but it will be dx over dx. What's dx over dx? It's 1. Okay, so it's pretty much the same. Pretty much the same thing. Okay, so like I said, it might be hypothetically, not necessarily on an actual test, which is what is it? It's 1 week from today. What do you know? It's time flies. The problems might be more complex hypothetically, and so that's what you see in the textbook is the problems that have more variables to worry about. And then they may have different names and so on, but usually you don't have more than 3. So once you learn how to do the simpler problems like this, then the rest are really not big of a challenge. Okay, so we have to keep moving, and the next topic is a little bit ahead of schedule, but I do believe that it is better to deal with it now, and that is the how to reverse differentiation. Every problem in mathematics can be reversed. If you're supposed to find something based on data, then you might reverse, and then that answer might be used as a data to solve the problem that goes backwards. It's so for example, evaluate x squared with x equal 2. Okay, that's one. If I reverse it, I could say find x such that x squared is equal to 4. So if you solve the problem on left, okay, so then the answer will be 4. Okay, but then you can take that solution and give it to somebody by hiding the relevant information. So if I'll take this and hide it. So the answer is of this problem is the answer is x squared is equal to 2 squared is equal to 4. Okay, so I take the answer which is 4 and then hide the information where it came from, and it comes from x equal 2, and then suddenly I have a new problem. Okay, so the problem has been solved in a very easy way. I mean, x squared at x equal 2, that's easy. You plug in x equal 2 and you have your answer 4. But not obviously in this course, but certainly at some point this kind of problem may have been a challenge. Okay, even though so easy, and this is way more complex. Reverse the order. Substitution versus solving an equation. That's the challenge. And you can think of a bunch of these very similar. For example, how about evaluate 2 to the x with x equals 3. Okay, so you solve the problem. So that's the problem. Okay, then you solve it, and then you have 2 cubed is equal to 8. Okay, you take the answer and use it as the data for the new problem, hiding the source of that answer. So so the question would be find. The other question would be find x such that 2 to the x is equal to 8. Okay, so imagine that you haven't solved this problem on left. The second problem would be somewhat of a challenge because you'd have to actually remember what is that number. I raise 2 to that number that it gives me 8. Okay, and that might take time to process. And the answer is actually that's how logarithm come up. So here the square roots appear as a new function because you want to learn how to solve those problems. In the second line, I have to invent a new function, logarithm, in order to solve those problems. So that's how it goes back and forth. And the inverse, you realize what we're talking about. We're talking about the inverse functions here. Inverse problem instead of reverse, it will be more appropriate called mathematically the inverse. So inverse is more complex problem. So if you feel differentiation is a hard problem to solve right now, imagine that if we reverse. Okay, so for example, evaluate, how about f prime of x for f of x equal to x squared. Okay, you solve it, and the answer is naturally f prime of x is equal to 2x. Okay, and then you create a opposite problem going backwards. Find f of x such that f prime of x is equal to 2x. Okay, so a problem, if not an easy problem, but it certainly will become an easy problem, that's on the left. In terms of a problem that is totally new, and at this point the only tool that we have for solving this problem is pretty much just remembering that at some point we did differentiation, and now we know we know the answer, so we can find the question for that answer. So so x squared. So if you remembered what's on the left, you can solve the problem on the right. Yes.
So is every derivative like unique? So like for each line or whatever, for each thing.
Each function has only one derivative. Yeah.
But can some of them share the same derivative?
Yes.
Okay.
Well, so that's why the good point, because then the answer is ambiguous. And the answer is there's a 2x and 2x plus 1. They are both good. Both have the same derivative because the difference between these two curves is negligible. It's just a shift, a vertical shift, so all the slopes are the same. But it's not unusual. It's not unusual because look at the first line. What can you say about the first line? In the first line, the second question. What's the answer?
2.
Got it? What about negative 2? And negative 2, right? So even with equations, you have the same ambiguity. You might have more than one answer. That's the difference between equations, between substitution and computation, which is unambiguous, and then when you reverse it, you might have more than one answer. It is not atypical at all. So imagine the trig functions, they will give you infinitely many answers right away. So this one gives you infinitely many answers, so you can just draw the same picture and draw the same curve, and it doesn't matter how many times you repeat, it will have the same exact shape. So you can even probably you can draw a curve, and well, I wonder if okay, and as long as that's not like that. As long as paste, okay, as long as they are oriented appropriately, one straight above the other, like this, these are two different functions, right? And yet they have the exact same derivative. Okay, so that kind of the ambiguity is not entirely it's not really that challenging. So I could put as many of these as I like. They all equally good as far as the derivative is concerned. It will produce the exact same derivative. Okay, so as I said, same derivative. So that is certainly an important insight into derivatives. Think about about that last line, a less theoretical way, but more practical, and that is the location and velocity. That is the relation. So if my f of x is my location, then f prime of x is my velocity. So if I know where I am, I can find my velocity, but also vice versa. If I know my velocity, I know where I am, except the answer is ambiguous. If I don't know where I have started driving or walking, then I won't know where I am. I only know the displacement, how far I went from the beginning of the point, and that is the difference between the endpoint of each of these curves and the beginning and the end point of these curves, which is the same. but the exact location requires your knowledge of the initial of your initial location. So if you know the initial location, it gives you one specific of these curves, and then the ambiguity is gone. Okay, so so that is the idea. Okay, and so we have to. This theorem is just as big, and in fact it runs through the end of this course, and then it's still in calculus 2 it still keeps going. So it's called integration. So this step is integration, as opposed to differentiation. Why is it integration versus differentiation? There is some addition involved in the integration business, and then that eventually explains the meaning of this word. But right now, it is easier to speak of the derivative instead of differentiation integration. It's easier to speak of derivative versus antiderivative. So finding the derivative of functions, as we have done, and now it's reverse. Given functions, find their antiderivative. In other words, so f from f to f prime, and here from say from f to some f capital, such that f capital prime is equal to f. Okay, so that's the difference. The first problem, the second problem, the first problem is direct. We have all of those rules. They really make ultimately, well, once you become comfortable with them, make solving differentiation problems straightforward. It might be tedious if the function is really complicated, but they can always be solved if you just follow the rules. Okay, anti-differentiation is not so easy. So let's the starting point is to look at to create a table, which is we need anyway. So we'll create a table of derivatives first. So derivatives. So we don't have too many, but we have a few. So for example, power formula: x to the r is equal to r xr minus 1. Okay, so as long as r is not equal to 0. Okay, so that's derivative. So I'm sorry, I missed the prime over here. So function on left, derivative on right. Well, maybe. Well, let's write it out first. Okay, so e to the x prime is equal to e to the x. ln x prime is equal to 1 over x. Cosine x prime is equal to negative sine x, and finally sine x prime is equal to cosine x. Okay, so these are the derivatives that we know to begin with, and combined with the like 5 rules of differentiation, it gives us unimaginable number of derivatives that we can find a fairly straightforward way. But now let's write it out in a different way, and what I mean is I want a table. I want a table of functions. So I'll put a function on left, and I put the derivative on right. So x to the r, derivative is r x r minus 1, r not equal to 0. E to the x, ln x, 1 over x. X not equal to 0, so let's not forget that. And then cosine x, negative sine x, sine x, cosine x. So okay, so and then the trick is, so that is very useful, and I hope you will eventually, but by the end of the semester, you certainly should remember these 5 formulas. They solve you all the problems. But now, what is that we are after? We're gonna read this table right to left. That is anti-differentiation, the anti-part. So instead of concentrating on left and progressing to the right, its derivative, we're looking at, we say, suppose the function that we're looking at is on the right. So function here, okay, its antiderivative on left. So that's not a bad start, actually. We have a list of antiderivatives right away. So derivative of cosine is sine, for example. Derivative of negative sine x is cosine x. Okay, so it is quite useful to begin with. Let me try, however, to create a table more convenient to use. I just want now to put it use this table, but now just we read right to left, left to right usually. So I wanna arrange this again. So let me try to take it. So this is okay. This one. This is no, wait a minute. This is gonna be my left column. Okay. This one. Copy. That is my left column. Paste. That is my left column. Okay. Now, what it used to be my left column becomes right column and vice versa. So now this is going to be my right column. Okay. As long as they are aligned. Wait a minute. Okay. Okay. So they are aligned. Okay. So let me now add what's missing. Like this. Okay, so this is my function on right, on left, and on right I have my antiderivative. Once again, if you don't remember what it is going the opposite direction of of differentiation. Okay, so there are things to be considered. This table is not, once you put it this way, it's not as convenient as the original. Okay, so why not? Well, first of all, if you look, this one is okay. This one is okay, right? This one is also okay, even though probably the 1 over x is undefined. So it's not okay yet. Okay, sine x cosine x is also okay, but what's missing is this part. Okay, so the meaning is, repeat it every time and many times. The answer is the ambiguity. That's how we take care of the ambiguity, because there is not a one answer, but there are infinitely many answers. So that is why you want to indicate that no matter what constant number you add, it is still an antiderivative. So e to the x plus c. I mean, think about it. If you differentiate, what you're going to get? You're going to e to the x, right? So that's, all of them are antiderivatives. So infinitely many antiderivatives, just like this picture over there. See, infinitely many of those curves. So we want to have them all, because we don't know which one we're going to need. Just like with motion, if you know your velocity, you know where you are, but not exactly. You know the pattern of behavior, but nothing else. So you don't know ahead of time. You want all of them, and that's how we have. Okay, so I will, the bottom is okay once again. Okay, so that's fine. This is also fine. The remaining two, so now this is fine and this is fine. Okay, and c is constant in all of them. The other two is not quite perfect, and well, you can tell me why. You see a problem? Let's look at 1 over x and logarithm. There's a problem there. You see it? Compare the domains. What's the domain of the logarithm? What do you mean? No, domain, the values of x for which the formula makes sense. 1 over x, this is the domain, right? Everything else is fine. What about the logarithm? Well, it has to be positive. You cannot have logarithm of a negative number. Okay? So that is why we have to add, to make sense of this, we still add plus c, but we have to put the absolute value there. That is not all, because we have to be, when there is a gap in the domain, we have to be careful. So then I have to add a caveat here, and the caveat is that the formula holds for every open interval in the domain. Let me show you a little picture to illustrate this, specifically for the logarithm. So 1 over x, and on the one hand, in logarithm, the logarithm of the absolute value. So the 1 over x looks like this. Remember the asymptotes? Well, that's not pretty. And then in the meantime, the logarithm of the absolute value looks like this. Okay. So what this caveat says is that we are throwing, once we throw out 0 out of consideration, so x cannot be equal to 0, then there is no relation between one and the one interval to the right of 0 and the other to the left of 0. So everything is happening in an entirely separate way, and therefore we cannot speak of antiderivative defined on the whole negative infinity infinity, but rather only on the interval, either one or the other interval. So if I try to, well, let me put it this way. This is an antiderivative. Might look like this. Okay, so remember the shift, the vertical shift that we have to carry out. That shift, the c, might depend on whether we are doing calculus to the left of 0 or to the right of 0. That's the only thing that we have to worry about, is if there is a gap in the function, then our antiderivative becomes discontinuous, and we really don't have a way around it, because it is really a hole in the domain of the original function. 1 over x has a hole in 0, which means that its domain is 2, and which means that there is no way we can make our antiderivative as a continuous function. Well, what does it mean? It means that just stay away from the 0, and don't try to get around it. And so you have like a separate calculus for positive values of x and separate for negative values of x. They have to be, so this is like on left, it's like not one function, it's like two functions. I guess this is the only way I can think of, I can explain it. As far as differentiation is concerned, or integration, these two functions do not connect into one. Okay? I hope that kind of helps a little. So with that caveat, we are okay with 1 over x. The same caveat applies to the first line as well. It does not apply to the rest of the lines, of the rows of our table, simply because all of the rest of the functions do not have any gaps in the domain. Okay, sine, cosine, exponential function, the domain is the whole thing. But when you have that function over there in the first line, it is also 1 over x has 0 whole, and the function in the first line is might have, when r is negative, or when r is, say, 0. When r is 0, then you have division, and when you have division, well, let's say -1. If r is -1, so if you have division, you once again have a hole in the domain of the function, and we are having pretty much the same problem. So everything is almost okay. So the first line actually requires some extra work in order to produce a formula that is as convenient. So let me put it this way. If I put There is really no room for me here. Let me try to squeeze it in. X, the coefficient is kind of stands in the way. So if you look at the original table over here, it is the simpler function was on the left, and then whatever happens, you end up with it on the right. Okay, and that's not what we have here. We have some uncomfortable r over here, which stands in the way. So I want to put x to the power of s, and s is not equal to 1. Okay, then its antiderivative will be 1 of s plus 1 x s plus 1. Okay, so that's just a slight modification of the original formula. It is once again to make sure that we don't divide by 0. We require s not equal to 1, and otherwise, and never forget plus c. Okay, so once again plus c is required. But once again, it is if we happen to have negative powers, we have division by 0, we have a gap in the domain, and that's why we have to be careful about that, not jumping over that gap and treating it as a single function. So with that, we can now we have a bunch of antiderivatives. We have 5, and well, actually, the first line has a bunch of them, more than one, because every r will give you a function. And now I just want to write out this in the standard, the integral notation. For antiderivatives, it's this symbol. So e to the x dx is equal to e to the x plus c, for example. Okay, so that's the notation we're going to be using. So not a lot early on, and then a lot at the end of the semester, and then pretty much differentiation and integration, they are equally important. So one cannot live without the other. Okay, so so the meaning of this is, let's see. So let's identify what this is. Dx simply indicates the same dx as in the Leibniz notation. X is the independent variable. Okay, then this is the integral sign. Okay, naturally this is, it's called the integrand. So in other words, the function that we were trying to find its antiderivative. Okay, and it's called the constant of integration. Okay, and then pretty much the answer is the essential part of the answer is this, is the function that precedes c. So because you know that there will be always c there, so as long as you don't forget to add it, you're fine. Okay, so that's what we are talking about, and what we want to have early on is a little bit of just first of all understanding of what the nature of the problem is, the going back and forth, the differentiation integration, and the ability to solve problems of motion, for example. Okay, so so if you know the velocity, and no matter if you know the velocity of your motion, and for every moment of time as a function, then you can figure out your location based on that. Okay, so that is a very important thing, and there might be, however, even more than that. Remember, we talked about multiple differentiations, so you can have multiple integrations as well. So what I have here in mind is remember location, say f, then its derivative is velocity. If I differentiate with respect to t or x, doesn't matter, t with respect to time, f prime, and then if I differentiate one more time, I have my acceleration, f double prime. Okay, so now if you think about, if we're talking about any kind of physics setup, what we usually know is not our location. We usually know forces. you know the forces, and therefore you know the acceleration. Remember the relation between the force and acceleration? What is it? Force and acceleration? And the mass?
Velocity.
What? No.
Velocity to accelerate.
Acceleration, force, and mass. That's right. Okay, force is mass times acceleration, one of the laws of Newton. Okay, so that is the typical, you might have, I don't know, you have gravity, you have a spring, you have a string affecting some body of mass m, and if you know the setup of all those forces involved, you will know the acceleration. Okay? And then that is the natural state of affairs. For example, you're throwing a ball, you know that there is nothing, you ignore everything else, and all there is the gravity. Okay? So, and then from that setup, you're proceeding in the direction exact opposite. You're progressing from acceleration to velocity. Like this. And that is, velocity is its antiderivative of acceleration. The answer is ambiguous unless you know the initial velocity. Okay? Then you do it one more time, and you from velocity you find the location, and that's once again anti-differentiation. And once again the answer is ambiguous unless you know your initial location. Okay, so that certain example explains why integration is more important than differentiation, because typically you know the setup, you don't know all the information, and then you know where you are at every moment of time, and then you can figure out how fast you're moving. Yes, of course you could, but really it's typically you're solving a problem that you know what the situation is, and you want to predict what's going to happen. So you throw a ball, you want to, at this speed, at this angle, you want to know where it's going to land. You're going from right to left. Okay? All right, so we'll resume tomorrow.